In Module 3, Section 5, we're going to take a look at roots and rational exponents. So far in your educational career, you've probably heard of square roots and maybe even cubes. So the definition of a square root is that the square root of some number a equals b. If b squared equals a. So for example, we know that the square root of 9 is 3 and 3 squared is 9. So what we haven't really discussed so far is some properties of square roots. So every positive real number has two square roots, one positive and one negative. Because if you remember correctly, like I can do 3 squared and I'm going to get 9. But if I do negative 3 squared, which is negative 3 times negative 3, I'm also going to get positive 9. So previously we just think, oh, the square root of 9 is 3. But now we have to think the square root of 9 could be positive or negative 3, depending on the scenario. Also, the square root of 0 is 0, which in symbols, you can see we have our square root symbol, 0 equals 0. So we use that square root symbol, which I will often call a radical, to denote the non-negative square root of a real negative. The non-negative square root is called the principal square root. It's the most commonly known one. The number under the radical is called the radicand. For example, the radicand in square root 25 or radical 25 is 25. And then for any real number c, such that c is greater than or equal to 0, if I square the square root of c, it equals c. I'm going to go in a little bit more detail on this one. Basically, what this problem is saying is if you square a square root, they cancel. Because the square is the inverse, of a square root and vice versa. It goes directly back to our original example where we said the square root of 9 is 3, 3 squared is 9. So if I were to do the square root of 9 squared, those would cancel and I'd just be left with 3. Okay. Let's take a look at some examples. We already know the square root of 16 is 4, because we know 4 times 4 is 16. Anytime we are simplifying a square root, we're going to assume that we're looking for the principal root, the positive one. Our next example, we have negative square root 64. So what we'll do is we'll take the square root of 64, which is 8, and we multiply it by what's in front, which is negative 8. We know 8 times 8 is 64, but we still have that negative in front. Now that is different than the square root of negative 9. Because in this case, the negative is underneath the radical. And this brings us back to our example above. Like if I did 3 times 3, we already know that's positive 9. Even if I tried negative 3 times negative 3, I'd get positive 9. And the whole entire point of the square root, it's a number multiplied by itself that gives you the number underneath the square root. So I can't do 3 and negative 3. So this cannot be simplified. At least not based off what we currently know about square roots. I can't simplify a negative underneath a square root. We will talk about later in Module 4 how to simplify negatives underneath the square root, but for right now, we can't. We can also look at division underneath a square root. We are allowed to break this up. I can take the square root of 64 and I can put the square root with the 121. Now I can take each square root separately and we'll get 8 over 11. We already seen 8 times 8 is 64, and then 11 times 11 is 121. Next we have the square root of 0.81. If you have a perfect square with a decimal, you can kind of treat it like if you were just looking at a regular number, because we know 9 times 9 is 81. So if I just add a decimal and a 0 in front, 0.09 times 0.09 is 0.81. So let's give us 0.09. In our last example, we have the square root of 12.7 squared. So remember, a square and a square root cancel, and I'm left with 12.7. So notice in every example I just did here, I did not have a decimal answer. Even when I had a fraction, I did not have a decimal answer. And with the decimal underneath the square root, yes, I had a decimal answer, but it's a decimal answer that actually is a perfect square. So when we're simplifying, the examples we just did were examples of perfect square roots. So it's a number whose square root is a whole number. For example, we know the square root of 49 is 7, but if I tried to take the square root of 2, there's no number that when I multiply it by itself I get 2. There is a decimal. If you used your calculator, it's not a nice decimal, so it's approximately 1.418. So 1.418 is not a whole number because it's a non-terminating decimal. But 7 is a whole number. It's an exact number. If I plug the square root of 49 in the calculator, it's going to give me exactly 7. The question becomes, what do we do if it's not a perfect square? So the square root of a perfect square is a rational number, which means I could represent it as a fraction. And the square root of a positive rational number that is not a perfect square is called an irrational number. So for example, the square root of 20 is irrational because 20 is not a perfect square. Square root of 2 is also irrational because 2 is not a perfect square. We can also do the same thing with cubic roots, which we already kind of looked at a little bit when we were doing our sum and difference of cubes formula. So the cube root, so the only difference between the definition is that we now have a cube root. So cube root of A equals B if B cubed equals A. So for example, the cube root of 8 is 2 because 2 cubed is 8, which means 2 times 2 times 2. Couple of the same properties of cube roots carry over for square roots, carry over for cube roots. The cube root of 0 is 0. 0 times 0 times 0. Next, we have the cube root of -8. Now, one of the things that doesn't carry over with square roots is we are allowed to have negatives underneath cube roots. There is a way to write -8 as the same number multiplied by itself 3 times. and that's going to be negative 2. So if I do negative 2 times negative 2 times negative 2, negative 2 times negative 2 we know is 4. But if I multiply it by another negative 2, it's going to make it negative again and give us negative 8. So we are allowed to take cube roots of cube roots of negative numbers. And our answer is going to be negative. What we can also do is add variables underneath our roots. So we're not always going to be dealing strictly with numbers. So if I have the cube root of negative 64x to the 6th, I have to work with what number times itself 3 times is going to give us negative 64. And that's going to be negative 4 times negative 4 times negative 4. When we're simplifying variables, it's a little bit different. So I'm going to write out x to the 6th, which is x times itself 6 times. When you're simplifying variables underneath a square root, you have to think in terms of how many groups of whatever your root you're taking are there in that variable. So if I have x to the 6th, I'm looking for how many groups of 3 there are. And I have one group of 3 here, and I have a second group of 3 here. So that tells me that the cube root of negative 64x to the 6th is negative 4x squared, because I have 2 groups of 3 in my x's. So we can generalize what we've just done to be any root. So I can say that the nth root of some number a is b if b raised to that power n equals a. This allows me to do root problems, square roots, cube roots, fourth roots, fifth roots. We're not really going to do any examples where the root gets higher than a fifth root. So we'll not likely do a lot of examples where you see anything that's bigger than a fifth root. So let's take a look at some examples of those. So we have the cube root of 27. So if I find a number that when I multiply it by itself 3 times and I get 27, it's going to be 3. Okay. For the fourth root of 625, I'm looking for a number that when I multiply it by itself 4 times, I get 625. And that's going to be 5 times 5 times 5 times 5. Then we have the cube root of x to the 6th. So again, if I were to write out my 6 x's, I'm then looking for groups of 3. So I have 1, 2 groups of 3, which is going to give me x squared. Another nice thing about our nth root rule is that you can always go backwards to find the answer. Like if you can't think of right away what's the fourth root of 625, you can start raising numbers to the power of 4 to figure out which one gives you 625. And that's another way that you can find an nth root. So what happens if we are taking a root or simplifying a root that isn't being raised to a whole number? It's being raised to a fraction, such as 1 over some number n. So that can actually be rewritten. So a to the 1 over n can be rewritten as taking the nth root of a. So when we raise a number or a variable to a fractional exponent, specifically where it's 1 over a number, that's the same thing as taking a root. So for example, 4 to the 1/2 is the same thing as the square root of 4 8 to the 1/3 is the same thing as the cube root of 8. Now, we typically won't write what's called the index, which is the number that indicates what root you're taking for a square root. So if I'm raising it to the 1/2 power, we just write square root 4. But if I raise it for any power bigger than that, I have to indicate that with that little 3 in front. Let's take a look at some examples. So we are going to rewrite each of these examples in radical notation, so using roots, and if possible, then simplify it. So 25 to the 1/2 is the same thing as the square root of 25, which we know to be 5. 27 to the 1/3 is the same thing as the cube root of 27, which we also know to be 3. This next example is a little bit tricky. So this is saying we're going to take the 5th root of x. Now the last examples we've done, we had x to the 6th, and I was able to break it down and simplify it further. I can't do that here. I only have one x underneath my root. And if I have a 5th root, that indicates I have to have 5 x's in order, I have to have a group of at least 5 x's in order to simplify it at all. So that's as simplified as it gets, 5th root of x. And then we have negative 27x to the 6th raised to the 1/3 power. So this is the cube root of negative 27x to the 6th. So the parentheses around negative 27x to the 6th means everything in that set of parentheses is being raised to the 1/3 power. So everything goes underneath my cube root. So that's going to give us negative 3. And then we've simplified x to the 6th, the cube root of x to the 6th, multiple times, and it'll be x squared. So what we've just taken a look at here is going to lead us to our next example. If I have some number a being raised to the power of m over n, so they're still being raised to a fractional exponent, but it's not 1 anymore. So it still becomes the n still becomes the root, but now, and I still have a, but now this entire thing is being raised to the power of m. So when m is specifically 1, anything raised to the power of 1 is just itself. But now we're saying, what if we raise it to some different power, like 2, 3, 4, so on and so forth. So that's what we're going to do in our next examples. We're going to go ahead and rewrite our numbers using radical notation, and then we're going to simplify them if possible. So 9 to the 3/2 is going to become the square root of 9 cubed. Now, when you're trying to decide what to do first, should I simplify under the square root or raise it to the power and then simplify it? It's kind of like when you have the choice of, do I multiply, when you're multiplying a fraction by a number, do I do the multiplication in the numerator first and then divide? Or do I go ahead and simplify the fraction by dividing first and then multiply? That's what we're doing here. Do I make the number smaller first by simplifying the root and then raising it to a power to make it bigger? Or do I make it bigger first by raising it to the power and then simplifying the root? And the answer is do the root first if you can. So we know the square root of 9 is 3, which we're then going to cube, and that's going to give us 27. If I had done it the other way and I had done 9 cubed first and then simplified it, I still would have gotten 27 as my answer. It's just a lot harder to think up, like, what's the square root of 9 cubed? I don't even know what 9 cubed is. Okay. Our next example, we have negative 32 being raised to the 2/5. So we're taking the 5th root of negative 32, and then we are squaring it. The 5th root of negative 32 is going to be negative 2, which we're then going to square, and it's going to give us 4. Last example, we have 1/4 to the 3/2. So that's going to be the square root of 1/4 and then cubed. So just like that example before, I can take the square root in the numerator and the denominator, which is going to give me 1/2, which I'm then going to cube. So the numerator gets cubed and the denominator gets cubed. So 1 cubed is 1 and 2 cubed is 8. And that's going to give us 1/8. Okay. So our last example is what happens if I raise a number to a negative fractional exponent. And this gets a little bit complicated. When you raise a number to a negative exponent, it actually turns it into a fraction. So that it's still going to be the nth root, and whatever is under that root is still going to be raised to the power of m. But because of the negative, what I'm going to put inside my root is actually going to be 1/a. So we're adding that extra step of creating a fraction. So our first example is 27 to the negative 2/3. So we're going to do the cube root of 1/27, and then we're going to raise it to the power of 2. So when I simplify the cube root of 1/27, I can kind of simplify it like I did the square root of 1/4. And basically figuring out the cube root of 1, which is 1, and then the cube root of 27, which is 3. I get 1/3, which I'm then going to square. And I square it just like I cubed the 1/2, and I get 1/9. Then we have negative 256 raised to the negative 3/4. This is a little bit different. So in all of the other examples where we've had a negative, it's been in a set of parentheses. In this case, it's not, which means the negative is actually going to stay outside the root and exponent I use here. So it's going to be negative, and then the 4th root of 1/256. Now, only that is being raised to the power of 3. So I'm going to find the 4th root of 1/256, which I believe is 1/6. No, 1/4? It's going to be 1/4. So 1/4, and then cubed. And then I'm going to cube 1/4. I'm still going to have that negative in front. I'm going to have 1/4 cubed, which is going to be 64. We're going to do a lot more examples of the negative exponents. So if you're still not comfortable with negative exponents and using that fraction, we're going to keep working with those more. At this point, I hope that you're comfortable with simplifying square roots, cube roots, possibly doing 4th roots or 5th roots, and then being able to take an expression, an exponential function, so an exponential expression, so something's being raised to an exponent, and convert it to its radical form and then simplify. Please let me know if you have any questions.